it is I think I have also mentioned this at the very beginning, that this course will give you the bridge between mathematics and computer science, how mathematical formats, formalisms, etc. can be used to represent all computations in our computers. Okay, so I think you are beginning to get some idea of what this course is about and how it is relevant. Okay, because using these structures, we can create mathematical models for various computation requirements. Okay, so finite automata, of course, you have seen the application before you came to theory of computation, in particularly in design of sequential systems, etc. You have seen how they can be represented by finite automata. And now you see context-free grammars. And Sir has also introduced, I know he has introduced the machines which can, the various classes of machines which can um, sort of implement or identify these various categories of languages. Okay, the finite automata, of course, we have discussed in detail, and push down automata, I know he has introduced. So you have seen how context-free grammars can also represent a class of languages which are called context-free languages. Okay, so we'll start from that point, but please remember, we are essentially taking a step back into regular languages, which is the first you can say type of language that we encountered. Okay, so let's look at regular grammars. Of course, since we are stepping back from context-free grammars, let's first take a quick look at how context-free grammars are defined. You know that any grammar, actually it's not just context-free grammar, but any grammar is represented by a four tuple or a quadruple, that is VTPS. Okay, you might have slight change in the nomenclature. Please do not be confused by that. These four components are the fundamental ones. Okay, so V represents the set of variables or non-terminals, okay, which actually make up the symbols of the strings that constitute the language. Okay, so you can also think of this as your input alphabet, the input alphabet which we had encountered in finite automata. Okay, so V I'm sorry, this is not, V is not the set of input alphabets. The input alphabets are the terminals, which are the symbols that make up the strings. And V are actually non-terminals, which are names which we give to certain places. Now, why we are calling these names and why we are calling them placeholders? Now, if you think of variables, I'm sure most of you will think of variables in terms of variables which you define while doing programming. Is that not? Okay, you know there are various classes of variables. Most of you, I find, will define most of the variables as integer variables. Okay, so what is this variable called x, which everyone has defined at some point in their lives? What is this variable x? This x is actually nothing but a placeholder which can, in which at runtime you can put various different values. And if you have defined it as an integer type variable, you can put various types of integer values in that placeholder. Okay, so it is a placeholder. Please remember, all variables are nothing but names you give to placeholders. So these are variable names. And these are non-terminal symbols. Why we are calling them non-terminals? If you have already done past trees or derivation trees, you know that terminals are the leaf nodes and non-terminals are the internal nodes, okay, which are named by these various variables. And P, sometimes it is also called R, okay, it's a set of rules or productions. P comes from productions, R comes from rules, okay. The rules usually are what are called rewrite rules. So whenever you encounter the left hand side, you can rewrite it or substitute it by the right hand side of the rule. Okay, so a rule in a context free grammar usually looks like what you can see on the left hand side. You will have a variable, single variable. On the right hand side, you have a string. Okay, a string of any length which could consist of symbols from variables and terminals. So variable symbols and terminal symbols. And the string could be the empty string also, that is epsilon. It could be a bigger string. It could be anything. But the left hand side always has to be a single variable. That is very, very important, and it defines the structure of a context-free grammar. And S is the start symbol. It's somewhat like your starting state in a finite automata. Okay, so VTPS, if you can define these four constituents completely, you have completely defined a context-free grammar. And because a context-free grammar defines a context-free language, you have defined a context-free language also. Okay, so a language is context-free if there exists a context-free grammar which defines it. Okay, but here, before we move ahead, why do we call it context-free? Remember, today I'm not going to discuss context-free grammar. I'm going to go into regular grammars, but your ideas should be very clear. I'm sure sir has told you something, but let me hear from you what you understand by context-free. Why this name context-free? Can anybody tell me? Yes, why call it context-free?
No restrictions.
No restriction on what? You are absolutely right, of course, but it's a very broad term which you have mentioned. So can you qualify it a little further?
Ma'am, no restrictions on like the right hand side, ma'am, specifically. Like the
Mm,
left hand side has to have one variable, ma'am, that is about the one restriction, but on the right hand side, there's no restrictions whatsoever.
no, 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 no. That is not correct at all. What you are saying is it is context free because of the structure of the productions. Actually, that is not correct. You are right about no restriction. It's not no restrictions. It is minimum restriction, you can say. Okay, so the restriction is actually on the left hand side. Okay, or the lack of restriction rather is on the left hand side of the rule. Notice that the left hand side of the rule is a variable, single variable. It does not tell you in what context you can rewrite that variable to the right hand side. Wherever that variable appears in any intermediate form, you may possibly substitute it by the right hand side of the production rule, and you should still be able to derive a string from it which belongs to the language. Okay, so these rules you have to write in such a way that the left hand side does not mention any context in which it can be replaced. Maybe there is a particular context, in that context only you want to apply this rule, that is not allowed. So it is restriction free. The rules can be applied whenever the variable on the left hand side of the rule appears in a intermediate form, or what is called a sentential form. Okay, so this lack of variable is what is making it context free, because context is not mentioned. And this is particularly relevant with respect to another class of grammars which is slightly more restricted, which is called context sensitive grammar, in which you will find on the left hand side it is not just a single variable. There is a form in which you can actually mention alpha v beta, and you can rewrite it to alpha, then whatever is the substitution, and beta. So in the context of alpha and beta to the left hand and right of this variable, only you can replace the variable. Okay, so that is a kind of context sensitive rewriting or context sensitive substitution. But in case of context free, context is not mentioned. Where you can apply the substitution rule is not mentioned. You can apply it anywhere, and you should be able to get the strings which belong to the language. Now, please remember, that means a very little restriction on the left hand side. And this lack of restriction is what makes context free grammars more difficult to create. Okay, because remember, when you have lots of rules defined for you, then finding a solution which meets those rules is easy. Okay, when there are no rules defined, then finding a solution which still gives you the solution that you require, that is more difficult. Restrictions actually are not a bad thing, they are a very good thing. Okay, because they restrict the domain in which we have to search for the solution. Okay, so because the restrictions are minimized, that is why context free grammars are more difficult. They are actually fewer languages which can be represented by context free grammars. So context free grammars are actually a subset of context sensitive grammar. Context sensitive grammars are wider, more extensive than context-free grammars. And of course, we add some more restrictions in where these grammars can be, how these grammars can be created, and then we get regular grammars. Okay, so that is the reason for context free, because the left hand side, or this production rules, these rewrite rules, can be applied wherever the left hand side appears in a string, an intermediate form during a derivation. Okay, please remember this. And how do we use these rules? If A rewrites to B, then XAY rewrites to XBY. Okay, so notice that what this X and Y is not restricted by the rule. The rule just says that A will rewrite to B. Okay, this A and B need not necessarily, B particularly does not have to be only a variable. It can be anything. It can even be a string. Okay, and you know that this we say it derives or derivates x by, and when you have a string of such rewrites or derivations, then you can say that S derives T. The string S produces string T. So a string X is generated by this grammar. Notice here, instead of T, we are writing sigma. Sigma is the symbol we had used to represent the input alphabet, if you remember. Okay, so that is because terminal symbols are the same as the inputs, these input symbols which create the input, which make up the input alphabet. Okay, and build up the strings of the language. So the language is defined, the language of grammar G is all those strings which can be derived from the start symbol S. The start symbol plays an important role, and you have to begin from the start symbol. The grammar is created such that beginning from the start symbol, you should be able to derive all the strings of the language. And there is only a very restricted class of languages which can be represented by such context-free grammars, and these are called context-free languages. Now let's take an example. So VTPS, we define as QF, we require two variables, possibly we could use more. Now, and terminal symbols are 0 and 1, we are just keeping it simple. And rules you can see, or the production rules are Q is the start symbol. Okay, so start symbol is Q, as is given here. So Q rewrites to either 00Q or 00F, and F will rewrite. So Q and F are the two variables. F will rewrite to 11F or to epsilon, which is the empty string. Okay, now looking at this, and since you have already worked with some grammars for quite some time, can you please tell me what kind of strings will be derived by this grammar?
Ma'am, what kind as in what classification or the strings itself?
Can you describe the strings which will be created by this grammar in English-like language?
Ma'am, a string of consecutive zeros and ones, ma'am.
Consecutive zeros and ones. Can you have zeros after ones?
No, ma'am. Like zeros and then ones.
How many zeros?
Even number.
Even number of zeros, even number of zeros, and even number of ones, followed by each other.
No, two ones, just two ones.
Just two ones? Any further? See, you are on the right track,
No,
but
no, ma'am,
your
not two ones,
description
ma'am.
is not
Ma'am,
complete yet.
Ma'am, more than two ones, ma'am, because F goes to 1 1 F, and then 1 1 F's F could also go to another 1 1. So
Yes, right. You're right. So how will you, what description will you give to the strings you can derive from this language?
It will be like if I were to write, it will be 0 to the power 2m, and then 1 to the power 2n.
0 to the power 2n and 1 to the power 2n, or some other number?
No, m, some other variable. No.
Okay, but can you qualify this n or m any further? Okay. I'll give you a hint. Can you derive the empty string from in this grammar? By this grammar?
I don't think empty strings will exist in this grammar.
Any other answer that's not correct? You cannot derive the empty string by this grammar.
Any n and m should be greater than 0. I mean,
Which one is greater than 0?
Number of zeros.
Number of zeros. Okay. And what about m?
M might be 0.
M can be 0. Yes. I think now we have got the final or complete description of this language. Okay. So it is even number of zeros followed by 0 or even number of ones. Is that correct? Or can you qualify it further? So you have even number of zeros, 2 or more, okay, followed by even number of ones, which could actually be 0 also. 0 or even number of ones. Is that correct? Anybody has any other suggestion to make? So is it a context-free language? What do you say? This language which has been defined, is it a context-free language?
Yes, ma'am.
Yes. Why?
Ma'am, because like for ma'am, as I said, ma'am, in the case of the F, ma'am, doesn't
Pardon?
require a I mean, as I said, in case of the F, ma'am, like F11, F could also go into like further ones. So that won't
That
be.
is not the correct answer. The answer should be yes, it is a context-free language because it is described by a context-free grammar. That is exactly what we said in the previous slide. See, language is context-free. See, look at this line. A language L is context-free if there exists a context-free grammar such that it is defined by that grammar, right? And here you can see this language we are defining by this context-free grammar. This grammar VTPS is a grammar. VTPS defines a grammar. Okay, so V is defined, T is defined, S is defined, and these rules that define the strings. Okay, so since we have a context-free grammar, notice that the rules have only variables on the left-hand side. So it is context-free. Okay, so it is a context-free language because it is defined by a context-free grammar. Now I'm asking you that now you know that what kind of strings. If you have got your notebooks out, and I hope all of you are sitting with open notebooks and pens and pencils. Okay, I want you to put down a few strings which belong to this language, and then you try and draw a regular expression or finite automata for this language and tell me whether it is possible. If it is possible, you might hold it up on your screen and tell me and I'll switch it on. I would like to see it on the screen. If you can draw a finite automata or you can write a regular expression which defines this language. First tell me, is it possible?
Yes, ma'am, it's possible, ma'am.
Yes, you are right. Can you tell me what is the regular expression?
Ma'am, 0 to the power 2m, 1 to the power 2n, m greater than 0.
That is not a regular expression. Regular expression does not allow you to raise anything to n.
Ma'am, 0, 0, 0, 0 star and 11 star.
1, 1 star, not 11. Yes, you are right. This is the correct answer. 0, 0, 0, 0 star, 1, 1 star. Okay, so this is a regular expression, you can see. Okay, raising something to the power n. See, we often use this to express strings, categories of strings, but this is not a regular expression. A regular expression, remember, has a very, very narrow structure. Okay, you can only use the operators plus and dot and clean closure. Okay, so remember, no other operator is used. For example, raising something to the power of something, that is counting, isn't it? It is not allowed. In that case, you could write 0n, 1n, why not? And you know that this is not a regular language. Okay, so this is a regular language also, and what is interesting is that the regular language is also defined by this context-free grammar. Okay, so that tells us that regular languages can also be defined by grammars which are context-free. Okay, but here, so every regular language can be defined by a context-free grammar. Very, very important, please remember. So let's look at the proof. So we have a regular language or a regular set, and remember, how have we defined a regular set? Any set of strings consisting of a language consisting of strings such that you can define it by either a finite automata, any kind, DFA, NFA, epsilon NFA, okay, because you can interchange between all the two, you know how to convert from one to the other, okay, or by a regular expression. Okay, so we can take any of these representations to define a regular set, just as we use a context-free grammar to define a context-free language. Okay, so regular language. So we have now a DFA which defines a regular set. So we can construct a context-free grammar. If we can construct a context-free grammar which defines this particular set, then we can say that every regular set is also a context-free set. So how to construct a grammar? You know that to define a grammar, you have to define 4 things: V, T, P, S, or T or sigma, whatever. Okay. So how will you define the production rules? Now notice this is mathematical. If you do not understand, please do not be worried, because we are going to revisit it very soon in this class itself. So now this you can see it is nothing but a transition in the finite automata. So delta is the transition function. So from state Q on input A, you go to state P. Okay, so these are all the transitions, all the arrows in the finite automata. You can actually convert them to rules. How will you convert them to rules? So if from state Q on seeing A, I go to state P, then I add the rule Q defines, or Q rewrites to AP. See, note here, Q and P are variables and A is a input symbol, terminal symbol. Okay, so if you have a transition like this, you can create a rule like this. Okay, so we are basically either deriving or consuming one input character at a time. Okay, and also if you are in a final state as defined in this given DFA M, okay, then you can add a production which says F rewrites to epsilon. That means basically remove that variable from the sentential from the derivation. Okay, and then you will be left with the terminal string which you have derived or which you can accept in the DFA. So if you create the rules like this, so you have basically produced, note that the left hand side of the rules which we have written are only variables. So this is also a context-free grammar, as we have defined context-free grammars. Okay, so we have basically, what we have done is we have created a context-free grammar for the regular set given to us in the form of a DFA. Okay, so let's see how this goes about. So if these are your transitions in the DFA, you can see that from S, on consuming input X1, you go to Q1. Okay, then your derivation from the context-free grammar which you have created will look something like this. From S, you can derive X1 Q1, and now you are in Q1. So next X2 Q2, but X1 you have already derived, so this is part of the string. Then X1, X2, X3, maybe Q3, and so on till the last symbol, and then you end up with X1, X2, etc. till Xn, and the final state F, which is Qn. Okay, and because it's a final state, accepting state, so you have a production rule of the form F rewrites to epsilon, and you can use this to remove this F from the sentential form or this intermediate form. I hope all of you understand what is a sentential form. What is a sentential form? How do you define a sentential form? Okay, a sentential form is all these intermediate forms in a derivation. I hope all of you have learned how to derive a string from the start symbol.
Yes, ma'am. Yes,
And you can write a derivation step by step, mentioning which rules you have applied.
yes, ma'am.
Okay, so these intermediate stages in a derivation, you'll note that they are made up of terminal as well as variable or non-terminal symbols. Okay, so these intermediate forms are called sentential forms. Why this term sentential? Because we are going to be using these grammars to define the sentence constructs in various languages, like for example English. Okay, so we will see that, and you will in fact use it very in great depth when you study compilers. Okay, so you'll be using this context-free grammar derivation. So that is how the sentential form term comes around. So sentential forms are nothing but these intermediate forms in the derivation. So see here, all these intermediate forms, x1 q1 or x1 x2 q2, then x1 x2 till xn, and finally f. Okay, and so when we come to this final sentential, or not a final, pre-final one, okay, we find that there's only one variable left, which is the final state. And final state, because it's the final state, we have already added a rule to remove this final state. Okay, so we can remove this final state and we are left with the string x1 to xn, which is the string derived from s, and it belongs to the language. And note here in this DFA on the left, it is exactly this string which has been consumed or identified or accepted by the DFA. Okay, so this is how a DFA can also be represented by a context-free grammar. Okay, so this context-free grammar represents exactly those strings which are accepted by the DFA. So this DFA and context-free grammar, they are actually equivalent. Okay, and since they are equivalent, so we can say that for every DFA, you can create a context-free grammar. So that means since a DFA represents a regular set and context-free grammar represents a context-free language, so you can say that every regular set is also a context-free set or a context-free language. Okay, so this is a very, very important realization or derivation. Okay, so this we have already seen, since there's a path from initial state to final state, which also corresponds to the derivation of the string s, x from starting from the start symbol s. Okay, so therefore exactly the same strings are being accepted or derived. So the languages are the same. So what this gives us is this very, very important corollary, that every regular language is also a context-free language. But remember, every context-free language is not necessarily a regular language, because you have already encountered some context-free languages which are not regular. Okay, and I know 0n, 1n is the example which you have discussed, and I'm sure you have discussed several more. Okay, but every regular language is a context-free language. So that tells us that regular language is a proper subset of context-free languages. Okay, but why proper? Because there are some elements which belong in this green area, okay, which are context-free but not regular. Example, 0 and 1n. Okay, is this clear? This much, is it clear to all of you? Can we proceed from here?
Yes, ma'am.
Okay. So now we are going to play around with regular languages and regular grammars. So now we know that you can produce a grammar to represent a regular language. But these grammars, they have a little more restriction and they are a little more qualified than your normal context-free grammars. Okay, so what are these regular grammars? Regular grammars are typically of the form either left linear or right linear. Please remember, they have two forms, and just as you can convert from an NFA to a DFA or a DFA to NFA, epsilon NFA, so on, similarly you can convert from left linear grammar to right linear grammar to left linear grammar, and so on, and of course from every grammar to a finite automata, and the reverse. So left linear grammars, how do we form the rules? The rules follow a particular structure. Of course, you can allow epsilon productions, and a single strings, W is a string of terminal. Okay, in some texts you will find they restrict it to a single terminal. It makes no difference. You can always derive it in that way also. Okay, or it could be a terminal string. It is either a single terminal or a terminal string, makes no difference. It's still a regular grammar. And right linear, if this terminal string at the end, you could have a single variable. A and B are single variables. Okay. And in case of left linear grammar, the first two are the same. Only here the single variable is on the left. Okay. So depending on the position of the variable, you call it either a right linear grammar or a left linear grammar. Okay. So let's take an example of what a left linear grammar looks like. I'm sorry, this is a right linear grammar. Right linear grammar. So we have this grammar here. S derives AS or BA. Okay, and A derives CA or epsilon. Okay, what kind of strings? Look at the derivation. So it produces strings of A. Okay, you can use AS as many times as you like to produce as many A's. Okay, and then when you don't want to produce any more A's, you replace S by BA. And then you replace this A by CA, and this you can do many times. And then finally, when you are done with producing as many C's as you like, okay, you can remove this A by using epsilon. Okay, so this is a right linear grammar which produces the language of this A star, B, C star, as you can see. Okay, so this is a regular expression. All of you clear on that? We have not used any other construct. So A star, B, C star, and this grammar produces strings of this form. Okay, so this regular expression and this right linear grammar. Why right linear? Because the variable is on the right. They produce the same kind of strings. Okay, and this you can see a sample derivation, just what I described, and you can also see that it is a rightmost derivation. I hope all of you understand what is a rightmost derivation. What is the other kind?
Leftmost derivation.
Yes. Okay. So in any sentential form, if you always pick the rightmost variable to expand, then you produce a rightmost derivation. And in every sentential form, if you always pick the leftmost variable to expand, then it's a leftmost derivation. Okay. So leftmost derivation and rightmost derivation, you can easily identify it. The trees look slightly different. That's all. So let's take another example. So we have on the left a right linear grammar, and on the right we have a left linear grammar. Actually, maybe I should have interchanged the two. So look at this right linear grammar. So S derives 0A. Then once you have got this A, you can rewrite it to 10A, 10A again, 10A, and you can see the derivation here is shown not in the form of a derivation but in the form of a derivation tree. Okay, and finally A, you can remove it by using epsilon. A goes to rewrites to epsilon. So what is the string? What is the string derived here?
Zero one one zero.
Okay, so that gives you a clue as to what kind of strings we can derive using this grammar. Okay, 0 1 0 1 0. So these are alternating zeros and ones, starting and ending with zeros, right?
Yes,
and on the right also, you can see this is a this is the left linear grammar, and here this S is on the left, and you have only S productions. We don't need an extra variable, but we are producing the same set of strings. So it is a grammar for the same language. One is a right linear grammar and one is a left linear grammar, but they express the same language. Okay, and the derivation tree looks slightly different. You can see it is a leftmost derivation, and it is going to look like this. This also produces the same string. Okay, 0 1 0 1 0. Can you see that, all of you? So these two grammars, they are expressing the same regular language. Okay, what is the regular expression for this?
0 1 0 star.
Yes, 0 1 0 in brackets star, whole star. Okay, that's good. So let's come to so this is about left linear grammar and right linear grammar. So there are two forms, both are regular grammars, both are interchangeable, and we are going to work with both of them. But for the present, you forget left linear grammars. Let's look at right linear grammars first. Okay. So right linear grammars generate regular languages. I know all of you are already convinced, but let's look at the theoretic form of it. Okay. So if you take a theorem like this, and this is, you can see it is an if and only if theorem. Okay, they always generate, that means a right linear grammar generates a regular language can be represented by a right linear grammar, so they are equivalent. Okay, and equivalence means it is, you have to prove it in two directions. Always remember that any equivalence based theorem means you have proof in two directions. Basically you have two proofs. Okay, so given a right linear grammar, show that it's a regular language by constructing a finite automata, and given a regular language in the form of a finite automata, construct a right linear grammar. Actually, the second part we have already done, but let's do it again, no problem. So the corollary is a language L is regular. So this is actually not a corollary, it is, you can say, just restating this theorem in a different manner. A language L is regular if and only if L can be generated by a regular grammar. So if and only if is what is giving us this two directional proof. Okay, please remember that. So what do we have to do? Given a regular grammar, show that you can create a finite automata for it, and given a finite automata, create a regular grammar for it. And in both cases, we are going to use right linear grammars first. Okay, so from a right linear grammar, create a finite automata. So suppose we have a right linear grammar, VTPS or V sigma PS, construct a finite automata. And how do you do it? Now look at this carefully. Note that the T is same as the input alphabet, okay, so sigma. And S is the start symbol. S is the start symbol, and here, and the set of variables, okay, will relate to the set of states in the finite automata. The set of states actually will be the set of variables, and we are adding a special final state. That's all. Okay, so all of these variables correspond to, or you can say map to, states in the finite automata. In addition, we add a extra accepting state, special, which is the final state, the only final state. Okay, so S, which is a variable, the start symbol S, which is a variable, is also one of the states of this finite automata, and that state is going to be our start state. So start symbol produces the start state. So that is simple. F is the new symbol denoting the final state, and the productions have three possible forms. Okay, so whenever you have, so what do we have? We have a right linear grammar, and we are going to create the finite automata. We have already created the states of the finite automata. We have designated which is the start state and which is the final state, a special final state. We now have to put in the transitions, that's all. Okay, and transitions, as you must have realized, they come from the production rules. Okay, so how do the production rules map to transitions in the finite automata? If you have a rule of the form A sigma, A rewrites to epsilon, sorry, not sigma, epsilon. Okay, then add the transition A sigma to F. That means from A, you should go to the final state on epsilon without consuming any input. If A rewrites to small a, then add the transition A to F, that is the final state, on the input symbol A, small a. And if A rewrites to AB, then add the transition delta, transition from state A, on consuming small a, you go to the state B. Okay, so this is actually just the opposite of what we have done previously. Okay, so I think it is better to talk in terms of an example here. Okay, before the example, let's look at the opposite direction. That is when you have a finite automata and you're creating a right linear grammar. Okay, so we have the finite automata, input alphabet same as T, okay, or sigma. Okay, and states remain the same. Q0 remains the star, becomes the start symbol, and P we have to produce. So we are doing just the opposite of what we have just done in the previous slide. Okay, so for each transition in the finite automata, so you now in the second case you are given the finite automata and you're producing the right linear grammar. So if you, for every transition, if you have a transition from Qi to Qj consuming A, then you construct the rule Qi to Qj with consuming A, that is producing A, Qj. And you add a rule of this form to the set of productions, the production rules. And for every state in which the destination is a final state, okay, for every state, it's not Qi, it is Qj, okay, it is Qj in F, okay, add the rule Qi goes to epsilon also, because you have to remove this particular variable from the sentential form. Okay, so now let's just look
in that
at,
case, it would be Qj goes to epsilon in P, right?
I think it is Qj. Okay, let's look at the example and let me clarify. I do not know why I wrote Qi. Let's look at it, okay, and we'll clarify it. Let's look at the first case first. First is, now note here the productions are giving rise to the transitions, and the second case, the transitions are giving rise to the productions. And this last part will clarify. Actually, there are 2 or 3 different ways in which you can create the construction. So this is one of them. Let's see which is given in this particular example. So what we are going to do is transform the right linear grammar, given right linear grammar. You can see, I think we have seen this before. This is A star, B, C star. Okay, and we are converting it to the equivalent finite automata. Now, all of you have done enough work with finite automata and regular expressions to be able to create the finite automata without any trouble. So if you have A star, you have this loop, because you can take this loop any number of times, then a single B and C star. Okay, and because there is this epsilon, okay, so from this A, you also have an epsilon transition to the final state. Okay, in some books, this construction is given slightly differently. What it says is that if you can remove it, then you make this itself the final state. So that is also possible. It is basically the same. Okay, so let's go back here. So what it says is, if there is a production of the form A goes to epsilon, then add the transition from A to the final state on epsilon. So that is what we have done here. If there is a transition, A goes to epsilon. So you add this transition, A goes to F on epsilon. Okay, so basically remove A from the sentential form. And you can see that by this set of rules, you can produce this finite automata. Okay. Now let's now look at this and see whether it should be Qi or Qj. Okay, so transform the following DFA into a right linear grammar. So we have been given a DFA. We have obviously taken very simple examples. So Q0, Q1, and you can see how many transitions are there. 1, 2, 3, 4. So V set of states Q0 and Q1. So these are the 2 variables. So what are our transitions? Let's go back to the rule. Qi gives rise to transitions A Qj if there is a gives rise to production A Qj if there is a transition from Qi to Qj on A. This one. Okay. So which are the rules which are produced by this? Q0 A Q1 A Q1, Q0 B Q0 B Q0. Okay, Q1 A Q1 Q1 A Q1, Q1 B Q0 Q1 B Q0, and epsilon. So this tells us, now let's go back again and clarify this. So if for every state Qi in F, add the rule Qi. Okay, so this should be, this is actually not related to any transition. Can you see that? The second rule, This is not related to the transition here. It is for every state in the finite automata, which is a final state. Add the rule Qi goes to epsilon. Is that clear? So this should not be Qj. This remains Qi.
Yes, ma'am.
Okay. So
Hello.
now it is clear.
Hello,
Okay?
ma'am.
Yes. Yes. Please
Ma'am,
ask.
similar to
Anybody
this.
ask?
Yes,
Yes.
ma'am. Similar to this rule,
Yes.
we can also change the rule in the first type, means right linear grammar to FA.
Yes, actually it can do that.
Yes,
In
ma'am.
fact, I think in your textbook it is a simpler form which is given, but this will also produce a DFA, maybe with some few extra unnecessary epsilon transitions, but it will still be the correct. In fact, you will find some constructions in which this extra final state F is not added. So Q and V remain the same. Okay, so let's forget that. Let's follow this construction which is given, shown here. This will give you a correct construction, and the other one is also correct. Okay, that might actually produce a slightly more compact DFA, in fact. So here, this is not wrong. This is not wrong. So it's Qi. If Qi is a final state, then you add this rule, Qi rewrites to epsilon, and it is not related to the transition. We had gone wrong there. Okay, so because Qi is a final state, as you can see here, Q1, so Q1 goes to epsilon. Okay, so I think this construction is very simple. The construction is actually very intuitive because you have worked so much with finite automata, you should have no problems with it. Okay, so what do we have here? From a right linear grammar, we produce a finite automata. Okay, it happens to be an epsilon finite automata with epsilon transitions, but you can always convert it back to a DFA. That's not a problem for you. And in this case, we have been given a DFA and we have constructed the right linear grammar for it. Can you construct a right linear grammar from an NFA? What do you think will happen? Will it be correct or will it be wrong?
Could you repeat the question, ma'am? My net got a bit glitchy, ma'am. That's why.
Louder, please. I can't hear you.
Could you repeat the question, ma'am? Actually, my net got cut off.
See, we have been given here a DFA.
Yes, ma'am.
From which we are creating the right linear grammar. All very good. I don't think any of you have any confusion in this. This is quite simple. But what if instead of a DFA, this had been an NFA or maybe even an epsilon NFA? Could you still produce a right linear grammar from it? Without converting it to a DFA, I mean. Directly, can you produce a right linear grammar? Will it be correct? What do you think? What do you feel?
Yes, ma'am. We can.
Yes, ma'am. It should be, ma'am, because there's already the epsilon condition is given, ma'am. Like in case there was an epsilon or anything of that sort.
Yes, somebody else was also speaking. Please tell me what you think. I find that in this class only very few people interact. That is not, that is all right, because usually everybody does not like to speak up. But I do not know how many people are really paying attention. I hope all of you are listening, even those who prefer to stay silent. So please tell me, some of you, some other people who usually do not speak, whether you think it will be correct if I convert an NFA directly to a regular grammar.
It would be correct, ma'am, if we only
right or wrong?
Yes, it is right.
It will be right. Okay. Anybody else? Actually, you are correct. It will still be correct. Okay, because you will just end up producing some extra productions. So if you have extra productions, extra rules, your derivations will be a little longer, but you still will be producing the same strings and you are representing the same language. So what this also tells you is that there is not just one grammar for a language. There can be many different grammars. Okay, so if I give you a language and ask you to create either a context-free grammar or a regular grammar for it, each of you could give me different answers and you could all be correct. Okay, So that is why this again brings us to the concept of a normal form. So context-free grammars or regular grammars also, they have what are called normal forms. And in fact, in the next few classes, SD sir will be discussing such normal forms, how you can simplify grammars, make them very compact so that they produce small derivations, remove useless things from them, and produce what are called normal forms. So some such normal forms have been proposed, and we will look at them in the next few discussions. So
Hello,
yes, so yes.
ma'am, how can there be two different right linear grammar?
Actually, this I can only explain with the help of an example, which I do not have to hand right at the moment. But you could have some extra epsilon transitions. Please remember, right linear grammar is not a normal form. You can have various different forms of right linear grammars. Actually, I'll try to find an example which I do not have in the slide at the moment. Okay, so I'll keep your question pending. Let me see if we can answer it at the end of the code. Let's just proceed for now. It is possible to have more than one right linear or even left linear grammar, just as it is possible to have more than one DFA for the same regular language. Isn't it possible to have more than one DFA? It is only the minimum DFA which is normal, please remember, which is unique. You can have so many different DFAs which are still deterministic and produce the same language. So that is why from each different DFA you can create. In fact, I can give this to you as an exercise. Let my students do the hard work. So take a language, a slightly more complicated regular expression, produce 2 or 3 different DFAs for it, and the grammars for them, right linear grammars, and you can see different right linear grammars for the same regular language. Okay, so treat it as a homework, an exercise which will clarify your concept of regular grammars. Meanwhile, I'll have to proceed because I'm running short of time. I have to proceed to left linear grammars. Okay, so till now we have discussed right linear grammars. Right linear grammars are slightly more convenient to use because you can directly convert the finite automata to right linear to finite automata, and so on. But left linear grammars also express the same languages, the same set of regular languages. Okay, and actually you can prove it theoretically using the closure properties. Do you remember closure properties? We have discussed closure properties of reversal, complementation, intersection, union, and so many different operations. Do you remember closure properties?
Yes, ma'am.
And we are going to use them here to prove that left linear grammars also produce regular languages. Okay, so what does this say? So a left linear grammar, now here actually I'm using a closure property which we have not discussed, which I'll be discussing after you have finished with your normal forms, which is the closure property on reversal for context-free languages. Okay, so what this says is that if you reverse the right-hand side of the productions in a context-free language, if you reverse all the right-hand sides, then you produce the reversed strings. Okay, so previously if you were producing strings starting with 1 and ending with 0, now you will produce strings starting with 0 and ending with 1s. Okay, so every right linear grammar, if you reverse the right-hand side, you produce a left linear grammar. You can see that. And because you have reversed the right-hand side, you have produced a grammar for the reversed language. Okay. Now, this reversed language is a right linear grammar. Reverse of a left linear grammar is a right linear grammar. Right linear grammar you can convert to finite automata. Then you can reverse the finite automata. Okay. So, and from the reversed finite automata, you can produce a grammar again, the right linear grammar for the original language. Okay. So let's see what it says. So if you do reversals twice, once with the grammar and once with the automata, okay, then you're producing the original language. It is like applying negation twice. Okay. So if you apply a negation to an already negated argument, then you produce the original argument, the original positive argument. Okay. So what we generally do when dealing with left linear grammars is apply reversal twice, once on the grammar and once on the automata. Okay. So suppose you have been given an automata and you are asked to produce a left linear grammar for it. What would you do? Remember, apply reversal first to the automata. How do you reverse the automata? How do you reverse a finite automata?
Ma'am, by making the other state as final state, starting state.
Yes, and reversing the direction of the arcs. Okay, so that is very simple. You make the initial state the final state the initial state. If you have more than one final state, you add a single one and epsilon productions to them, and then you reverse all the arcs. Okay, so try to remember that diagram which I had given you. If you remember that diagram, everything becomes very clear. So what are we trying to do? Given a finite automata, we have to produce a left linear grammar for that language. So apply reversal to the finite automata, produce the right linear grammar for this reversed finite automata, then apply reversal to the grammar to get the left linear grammar. Okay. So 2 reversals will give you anything you want to do with left linear grammars. Remember that. Okay. Now, for example, so you have a left linear grammar, and the derivation, for example, for the string ABC in this is C, assuming C is the start string. Okay, C to BC to A, so ABC. This is a leftmost derivation because it's a left linear grammar. Then what do? Reverse the grammar. The right regular grammar is the rules of the form just reversed. Okay, so this same rules, you have reversed them all and you get this grammar. And it produces the reverse language. So create a finite automata for the language produced by this, because finite automata for a right linear grammar, you already know how to do it. So now that you have reversed the rules and it has become a right linear grammar, you create the finite automata for it. Okay. Once you have the finite automata, you reverse the finite automata. Okay. Then compute the reversed finite automata and interchange the start state and final state and reverse the arrows. Okay, so this finite automata which you end up with, the reversed finite automata, is the finite automata for the original left linear grammar. Is this clear? So please remember, right linear grammars directly to finite automata, direct construction we have seen. Left linear grammars, you have to go via a right linear grammar, and you have to apply reversal once to the grammar and once to the automata. Is this clear? See, so I have an example here. This again, I think it's an example we have already seen. Have we seen this example? Something similar. Okay, so these are also strings of 1001. Okay. Yes. Okay. So it will produce the string 1001. Only one string to it. Okay. And NFA, this is not a proper NFA. It is what is called a string NFA, which accepts not just a single symbol on a transition, but a string on a transition. Okay. So, but you can of course expand this to a proper NFA easily. Now this NFA accepts the reversed string. This is not a good example because the string is a palindrome. And then you reverse the grammar itself to produce the reversed. Okay. So once you have produced this language, then you reverse the language. It's given here in the form of a regular expression. And then this NFA produces, accepts the reversed language, and you produce a grammar for it. So you have, this part is actually just to show you how the regular expression is also inverting. But this NFA, you have reversed it to get this NFA, and from this you get the right linear grammar. Reverse the right linear grammar to get the left linear grammar for the original language. Which is the original language? This language. Okay. So please remember, just to summarize, all regular sets can be produced by context-free grammars. Only these grammars are slightly more specialized. Okay, they are either left linear grammars or right linear grammars. So these grammars are called, sometimes they're also called left regular grammars and right regular grammars. So these are this left linear grammar and right linear grammar are called regular grammars. Okay, right linear grammar to finite automata, straightforward conversion. Finite automata to right linear grammar, straightforward conversion. Okay. Left linear grammar, if you have to deal with it, go via a right linear grammar, which is the reverse of the grammar which you have been given. Okay. So finite automata to left linear grammar. Once you apply reversal to the automata and once to the grammar produced. Okay. Left linear grammar to finite automata. First you reverse the grammar, produce the automata, then reverse the automata. Okay, so 2 reversals every time. Please remember, left linear grammar, when you are working with left linear grammars, you require 2 reversals, one on the finite automata and one on the grammar itself. And this reversal operation on grammars, that is reversing the right hand side, to produce the reversed strings, this is a reversal operation. We will encounter this again when we do closure properties for context free languages. Okay. So let's stop here. The example which I wish I could have for you. If I have another class, maybe if I remember, I will show it to you. Okay, but you can actually try to create the example yourself. And if somebody creates the example and mails it to me, I'll be very, very happy. So what you are going to do is take a regular expression, create 2 different DFAs for it. Create 2 DFA, don't bother with NFA. And from each DFA, or if it's an NFA also, it doesn't matter. From each finite automata, 2 different finite automata, you create the regular grammar. Just keep it right linear grammar and show that different right linear grammars are possible for a given regular language. Okay, so will you do it?
Yes, ma'am.
If any of you sends me a scan of how you work it out, I'll be extremely happy. I'm not making it mandatory, but I'll expect it from you. Okay. Okay. Now, before I stop this class, Shubhrajit sir had asked me to tell you, and I was also a little concerned. So I feel that we are moving a little slow in this course because there's quite a lot to be covered, and it is not really good to go very fast. But we would not like to leave the course half covered. Okay, we would like to take it to its natural conclusion till undecidability. So it is possible that we might be requiring a few extra classes. And what sir and I both felt that if we can fix a time in the week, then from next week onwards, we'll make it a regular weekly class. Okay, that's an extra class. It's not official, but as far as this course is concerned, I think we are going to require 3 classes per week to finish up the rest in time. So, where is your CR? Abhishek, are you
next week we
here?
have our CA2 exams, ma'am.
Okay. Now, Abhishek, I'm going to give you. Are you there? No, he's not responding. I think. So whatever it is, you please tell your CR. Okay, next week if we have exams, that's fine. But if not, from next week itself, we will start an extra class, which is going to be at a fixed time for every week. So find us a free slot when we can take the class, and that slot will be fixed for us every week. It will be like a regular scheduled class. Okay, because 2 classes per week is not going to be enough to complete this course.
Hello,
so
ma'am.
we feel, yes.
Ma'am, my mic wasn't working. Sorry, ma'am.
Okay, that's not a problem. Please find me a blank slot. Okay, when everybody is free, all the 3 sections. I know I'm giving you a huge responsibility, but please do it for us. Find us a blank slot where all the 3 sections are free and fix that slot for us. Okay, but before fixing, of course, talk to SD and me so that we are also free. And we will fix this slot for TOC class from next week onwards.
Okay, ma'am.
Okay, so Abhishek, I'm giving you an extra responsibility, but please do it. Okay,
Yes, ma'am.
and all of you, please cooperate with us so that we can finish the course in a proper manner within due time. Okay, because you have exams coming up, I think mid-sem next week. And after that, of course, the semesters are also not too far away, but we still have a very significant part of the course left to be covered. Okay, we would like to do it in the best possible manner, both Shubhrajit sir and myself. Right? Anybody has anything to say? I'll make the PPTs available on the Moodle website, so you can get it from there. And if next week are your exams, then we'll give you the notice in due time. Okay, so we'll stop here today. Thank you.
Thank you, ma'am.